So I'm here to introduce, thank you for the kind introduction, and I'm here to introduce our first speaker, and Mary Beth Hueste. Mary Beth Hueste is the Truman R. Jones Professor in the Zachary Department of Civil and Environmental Engineering at Texas A&M University. Much of her research is focused on furthering the understanding of the use of new materials and designs for bridge structures with a focus on pre-stressed concrete bridge systems. Dr. Hueste is a fellow of the American Concrete Institute and has been actively involved in a number of ACI committees throughout her academic career.
Thank you very much for the introduction and for the opportunity to be part of the U.S.-Japan workshop. Very excited to present some of the work that we've been doing at Texas A&M University on ultra-high performance concrete, specifically for pretensioned bridge girder applications. The work has been sponsored by the Texas Department of Transportation, and I have a number of colleagues to thank for their part in this work, including Anal Mokapadye, John Manders, Stefan Hurlebaus, who are my colleagues there at Texas A&M and TTI, along with the students, Amreen Fatima, Hyunki Hong, Brittany Cooper, and Jay Shah, and our postdoc, Tevik Turtsioglu. So this is a 4-year effort, and so today I'll try to consolidate that down into about 20 or 25 minutes or so and give you some of the highlights, and then we'll talk a little bit about where you can find some reports coming out soon. So we'll talk first about the research objectives, and some of the overarching objectives of this project were really to investigate for the first time the use of UHPC for the Texas Department of Transportation for their pre-stressed bridge girders. And so they wanted to start looking into using this material as part of the girders themselves. They had a little bit of experience in the use of UHPC in connections and smaller pores. But the idea was to move to structural components. And so the first thing was that they wanted to look into developing a non-proprietary UHPC mixture to reduce the cost of using UHPC for large members, and also to specifically tailor the mix towards high early strength concrete needed for pretension bridge girders. So as part of that development of the mixture, we also needed to implement it into a precast production process, and so we moved it from the laboratory to the precast plant, and then finally cast girders and tested them to look at the structural performance. So part one of this talk will focus on the production and development of the non-proprietary UHPC mixtures. And here I just wanted to point out that when looking at the workability of these mixtures, we are doing the slump flow tests, looking at the flow in terms of the diameter of the flow, similar to what you might do for self-consolidating concrete, but using a smaller volume slump cone, if you would like to call it that we use here on this brass circular plate. And so we're measuring slump flows on the order of about 9 to 11 inches typically. So in order to get started on this project, it was very wide open and we needed to narrow down a bit. So we looked into the industry input in Texas to see, what kind of materials are readily available to us to produce UHPC. Some of the materials that were identified for precast concrete were type 3 cement, was typically used in the plants for high early strength for these types of girders. Fly ash was available in Texas. They also pointed out, there are different types of high range water reducing admixtures. They vary by plant, and so that is one of the variables. And then natural sand. So in starting out in our laboratory mixes, we did start out doing some sieving of the sand. We did some oven drying, but when we got to the plant, we soon realized that that is not going to be possible, and so we had to look at the use of natural sand as it comes from the pile at the plant. Curing was another issue that we asked about, and because the producers in Texas really don't need to use heat treatment, they preferred not to have a situation where they're required to use heat treatment. And so we looked at trying to do this without heat treatment. Pre-stressing's transfer also needed to be maintained within the first day to allow production to continue and turn over the precasting beds. daily, and so the desire was to keep that at 16 to 20 hours for release after casting. And then mixing and placement, some of the items to consider that we looked at were recently PCI has been sponsoring a project on UHPC as well and working with precasters, and one of their recommendations was to use about 50% of the mixer capacity to ensure that there's enough energy to actually mix the UHPC, which is required. We also looked at properties and durability requirements, such as sufficient flow spread needed to be maintained. We looked at some values in the literature initially for that. Mechanical properties, we did a feasibility design study with typical TxDOT bridge girder sections, mainly the Texas shapes, which are eye girders with a wider top flange and a fairly narrow web of about 9 inches. And those girders, when we tried to kind of push them to higher limits using UHPC, we found that a good release strength would be in the range of 12 to 14 KSI with a concrete strength at service of 18 to 20. And then, of course, we wanted to look at the durability and ensure that the expected good durability properties of UHPC, due to the very highly dense matrix, would be maintained in our mix. So the big challenge here, that might be a little bit different than some projects, was to get that high early strength that was needed for release without heat treatment. So this is just a look at the proportions of our mixture. You see the constituents on the left column here. The proprietary UHPC, that's I think pretty well known, is listed here. This is based on proportions that we got from a FHWA report. And then our UHPC mixture that we felt worked well overall is listed here. I would say that there is a very high cement content in our UHPC mix because of the high early strength that we needed. However, as you'll see later, the service life is quite good, so there is some balancing in terms of sustainability aspects. We do have silica fume. We are using fly ash rather than ground quartz. We are using just natural sand with a number 4 maximum. Water to cement ratio is a little bit higher for our mix. This is our HRWR and so on. Steel fibers, this is something that we looked into. We thought that we would at least try to reduce the steel fiber content a little bit to see if we could make that work well in order to reduce the overall cost of the UHPC, because the fibers are a big part of that cost. And so based on some of the direct tension testing that we did to compare, we felt like we could start with that 1.5% volume. Certainly you can use higher volumes of fibers and enhance the tension performance, but we were trying to meet some minimum requirements and we're able to do that. This is a look at the steel fibers. They're very fine, kind of needle-like fibers of a 1/2 inch length. So a look at the production of the UHPC girder in terms of mixing. We started out with a 3 cubic yard mix, so about 50% of the capacity of the mixer. And this is a timeline of the mixing time. And as we're going along that timeline, we can see the addition of different constituents. This is just a look into the existing twin shaft mixer at the precast plant that we were using. And so I want to just thank Hardened, which is a precast plant in San Marcos, Texas, that helped us out and allowed us to come in and mix UHPC in their mixers. So that was a big ask, and so that was very nice of them. As we get started, we're doing a dry mix of cement, silica fume, and fly ash. That's mixed for about 3 minutes, and then we move to the water addition for 2 minutes of mixing, followed by HRWR. So after about a total of 9 minutes, we started to see the turnover of the mix, so it was similar to what we saw in the lab. And then you'll see that we're adding the wet sand. There were some adjustments made because of the addition of wet sand from the plant, and so we found that by adding it at this stage after the paste had combined, worked well. We did hold back a little bit of the cement because it is such a dry mix. We needed some of the water from the wet sand to combine with the cement, and we didn't want it to be too dry at the beginning as we initially added water. So that was the reason for this what we call the tail cement. Then we're adding steel fibers. This took about 8 minutes, and that was about as optimal as we could get in this situation where we didn't have any kind of automatic conveying of the fibers into the mixer. We had to add these by hand, and so it was a manual job that we did. We did follow some of the guidelines coming out of the PCI study, which was the idea of using a screen over the mouth of the mixer so that we could pour the fibers on top of that screen and then vibrate them into the mixer, and that worked well. And so finally, after about 19 minutes, we conduct a flow test and then double check the workability, that it's not flowing too much where we're worried about fibers settling, and that it's not too stiff, that it's going to be difficult to place. And then this is going to be discharged into a Tucker-built truck at the plant where they convey it or bring it back to the beds where the precast girders are being cast. So this is just a quick video showing that casting of our second girder specimen. You can see that, it's a very flowable mix. There are no coarse aggregates in this mix, and so it's a very fine particle, dense, well-packed matrix that's designed such that it has very low porosity after it's hardened. As you can see, they're just kind of topping off the girder at this point, and it's flowing down into some of the adjacent areas that were a little bit lower. There's issues in terms of composite behavior that we looked at because the interface is quite smooth, and so we did try doing a little bit of roughening after the concrete hardened slightly, but we found that most of that just kind of scales off. So there's been some studies on other options, but you'll see a little bit later that we're using some steel reinforcement across the interface to provide composite action. So this is a look at compressive strengths. We did have, a requirement at 1 day as well as 28 days. By and large, if we look at the various bars that we're showing here, lab mixes in red are the plant trial batch. Texas 34s and 54 are the girders that we cast individually on different dates. And then we did a lab mix with a new cement that was being used at the plant sort of after we cast the 54 to kind of make sure that in the lab we were getting similar results. And so for 1 day, we're doing fine in terms of getting that required early release strength. Because of that high early strength, it's interesting that we're not seeing as much increase over time, but we are hitting the high early and by and large hitting the target strength at 28 days. And so with that, I can also mention that we had some additional hardened properties that we looked at, including elastic modulus. We did compare the values we got from the MOE testing and found that this is, a little bit lower. It's not directly proportional to the square root of F prime C like we have in the ACI code. As we get into UHPC, it's a little lower, but it is consistent with the literature. So we're in the range of 6,300 to 7,400 for our mixes, the various batches. We did uniaxial tension strength testing. This is the direct tension setup, which was recommended by FHWA, and I understand there's a AASHTO standard now for this test method. And then we also followed the inferred tension bending test setup, which is essentially looking at tension strength using a flexural bending test and also looking at ductility. So in the uniaxial tension test setup, we do measure deformations as we do in the flexural setup. This middle test, the uniaxial tension test, is a little bit difficult. I think it takes a lot of practice and lessons learned because you are testing a concrete prism in tension, and sometimes it breaks outside the area where your LVDTs are located and so on. So what we found is that on average, we were sometimes a little bit lower than our target strength, but individual specimens where we had a successful test were meeting the required strength. So we felt like that we were getting reasonable results. So as we look at other information here, durability testing, I have just a quick summary. We looked at resistivity testing, rapid chloride penetration tests, ASR, freeze thaw, scaling, abrasion resistance, and then at the end we did a service life prediction. What we found is that all of these measures came out very well for the UHPC. Very low resistivity, negligible, chloride penetration, and all the measures from these standardized tests were what we would expect for UHPC for this type of material. This plot is just showing the expansion strain versus days for several mixes that were compared. The one that you see in green is actually a conventional concrete with reactive sand, and then these flat lines are showing the expansion of UHPC with both non-reactive sand as well as a reactive sand. And because of just a very little water availability, we are not seeing any ASR issues in this mix based on our lab testing. We also looked at fiber distribution and wanted to see how well the fibers were distributed in our girder specimens. So after we tested the girders, we took some cores through the section of the web, and these green rectangles just show where these various X-ray CT images are being taken. We do see some different alignments of the fibers in different locations, but overall we're seeing good distribution of the fibers, and then perhaps depending on how the pour was done in the direction of the pour, we may have a little bit of alignment in some of these cores. The one that we see here on the right is just showing X-ray CT versus an infrared image of the same core. And this particular one was from our Texas 54 specimen. We did have a fairly stiff mix that came out on that particular batch, and so we were actually doing a little adjusting to get the flow up a little bit. So it took a little bit of time between that batch and the next one. So what we think is maybe we have a little bit of an elephant skin formation, which is sort of the drying of the surface of the UHPC that kind of creates a thick skin. And so that may have led to a little bit of fiber settlement here. I think the good news is that when we tested the girder, we really didn't see any issues resulting from this. So this is a cost analysis, just to kind of wrap up the material side of the UHPC study, is that when we did a cost analysis back in 2020, we were coming up with about $600 per cubic yard. This is comparing well, with some of the other studies that range from about $560 to a little over $1,100 per cubic yard. Proprietary mixes could be on the order of $2,000 per cubic yard, which may be okay as we're looking at smaller volumes, but we might, be interested in trying to bring that cost down for something like a girder where we have a fairly large volume. And so that was what TxDOT was interested in. And we can see that this orange part of the pie chart is the steel fiber cost. So that is, again, a big part of the total cost. So if we wanted to go to 2% fibers, we would just need to increase that cost a bit as well. But we're hoping that in the US there will be more fiber availability. At the time that we were doing the research, we did have to go overseas for our fibers, but I understand now that we have more available here domestically, which should hopefully help with the cost competitiveness of UHPC. So again, this is just a little bit of a summary of some of the things I highlighted, but what I want to emphasize is mainly just that we were able to develop a non-proprietary UHPC mixture that could be used, and we've been working with the precasters to implement that into production and see how that works. I think they have a lot to think about in terms of the implementation stage, but so far we've at least proven that we get some good results with those girders that we cast so far. And then this is just a look at the structural full-scale testing. This is our Texas 70 girder in our high bay lab at Texas A&M University. It's filling up a good part of the length of the lab, so it's a little hard to appreciate the size, but that's 70 inches deep, so I guess almost 2 meters, along with an 8.5-inch deck. One of the things that we wanted to do, TxDOT's desire was to look specifically at the girder being UHPC while keeping the deck the same as what they typically use now. So that meant that we needed a conventional concrete deck on that girder so that we really could understand the performance in the field. So I think as we move forward, there may be ways to make that section and the bridge even more efficient with UHPC. But again, this is sort of that first step that we're looking at. So here are 3 girders that we cast at the precast plant, and then we added the cast-in-place deck in the lab. So we have a Texas 34. It's a little hard to see, but all the strands on this are straight strands through the bottom flange. We also have a Texas 34 with some Harped strands, and then a Texas 54 with Harped strands. And all of these were tested with a deck. We looked at each one with Flexure and Shear. So we had 3 total tests, 1 shear test at each girder end. And I just wanted to highlight some results from the Texas 54 girder today. This is a set of cross sections of the girder along with the elevation view. So you can get an idea of what the harping looks like in the 54-inch girder, as well as the shape of the section. So again, this is an I girder shape that's used in many of the bridges in Texas and similar to other states. We do have some harping. It's just 8 strands out of 48 total. The specimen span to bearing center line to bearing center line is 68.5 feet. But the loadings that we're mimicking are based on a full-scale design of about 120-foot span. And so one thing that I want to point out is that on one half of the span, we do have some web reinforcement, which are called R-bars in the Texas standards. Those R-bars usually will come up and become part of the composite interface shear steel. Because we went to just minimum reinforcement here, so 24-inch spacing, that's not as closely spaced as typically done in conventional girders. That might be more like 6 to 12 inches. So we are supplementing that with some what we're calling UC bars. And these UC bars are 180-degree hooks that we are on one half of the span adding 2 of those to each R bar. And at the other side, we don't have any R bars, no web, mild steel, but we do have these hooked bars in groups of bundles of 3. So we're trying to put in enough strength for interface shear transfer, and they're spaced far enough apart to help with the casting. So just a few highlights of the testing. We tested in Flexure, which meant that we were loading here at the center of the girder. We have a chart here showing the total load, so that would be each actuator added together. So we're going up to about 800 kips total load. We have a black dash line, which is our predicted performance, and we have a blue solid line showing the experimental values that we're measuring. And the horizontal lines are showing decompression, service demand, cracking, and factor demand. And we did see the first sign of a flexural crack just above factor demand loads. So we felt like that was a pretty good outcome, that up to factored loading, we did not see any flexural cracks forming. As we continued on up, we see the green dash line, which is our nominal value that we're getting from our code prediction, and then we kept going beyond that. It's a little hard to see the photo here, but the cracks are very tiny, distributed cracks that we're reaching at this high load, well beyond the factored load. For shear, we do have 2 shear tests, 1 at each end. So you can see in the schematic here, we're moving to the minimum web reinforcement end to test, and we actually are loading up to 460,000 pounds per actuator at that end. And that gives us a total shear of almost 800,000 pounds across that web as we went to the maximum loading. We did get some cracks, of course, as we got to those high loads. We were trying to see how it was going to fail. And so as we get to this point, it's starting to bend over. We probably could have gone a little bit further, but we wanted to test the other end without having to put in an internal support. So again, we were able to predict very closely the expected shear capacity. And I just want to note that the factored demand is way down here. The service demand is about 200 kips, and so we got up to almost 800. So when we had the case with no web reinforcement at the end, it is also similar that we're reaching, close to 800 kips. We're missing a little bit of shear reinforcement, so we didn't get quite up to that same value. But I think you'll see that the crack looks a little bit more dramatic there, and I can tell you from being in the lab when it was being tested that it doesn't give you as much ductility when you do not have the shear reinforcement. So there are some benefits to that minimum shear reinforcement being in the web. And me being a little bit conservative, I kind of like having it there. But clearly we are getting some very high strengths even without it. And then finally, this slide is just a little bit of a comparison of when we tested the 3 different girders and shear at the unreinforced end, the reinforced end, and then in Flexure. And mainly, I just want to point out that the experimental capacity was either higher or very close to the predicted value. So we have a good understanding of how to predict the strength of these members. That was validated from the experiments. I would say that it helps to have the direct tension test results. Of course, you could have a qualified mix where you at least have an expected tension value. That would help you with that. And then some of these other values are just the service, the factored load demand, and then the nominal capacity, which is essentially based on the AASHTO guidance that's coming out right now for UHPC. So again, just to wrap up, I think in our design investigation, wasn't able to share too much about that, but we were able to show that with UHPC, we can take the same cross sections and make longer spans. We can maybe take out an extra girder in the and have more load per girder. So there's ways to make the superstructure more efficient with this higher strength material. The durability is also very beneficial in looking at service life. In terms of the structural performance, flexural performance was quite good. We did not see cracking up to factored demand. And then we also were able to get some additional reserve capacity. Shear performance was also, I think, quite good. It was interesting to finally get a chance to check this in full scale at the end of this project. And finally, our composite action worked well in terms of the interface steel that we provided there. We saw just a little bit of slip that happened after factored loading, but that was, I think, just a little bit of the release at the interface rather than any kind of structural problem. So with all that, I just want to thank you for your attention. Want to thank the research team and our sponsor, Texas Department of Transportation, and also mentioning that we are wrapping up this project and the reports right now. So if you're interested, I think those should be published in the next few months and available online. And so again, thank you, and I look forward to any questions that you have.
What would have happened if we replaced fly ash with slag? Do you think we'll get the same kind of results?
So I think that we could certainly work with that. I'm not the materials expert on the project necessarily, but I know that there's a lot of different options for different, replacement materials. The main thing is to have some of these very fine materials that help fill in all the voids within this fine matrix. So I think that's a good question that could be investigated further. I know that this is becoming more and more of an issue around the country, so perhaps, there will be less fly ash available, and that would be a good option to investigate, yeah.
In terms of prediction of the lifespan of the UHPC expansion, wouldn't autogeneous shrinkage pose a problem to UHPC with the low presence of water content and the high probability that it will shrink and shrink due to that purpose?
Yeah, I think that, we did do some measurements of autogeneous shrinkage and total shrinkage, and so we have quantified that. If I recall correctly, it may have been about half of the total shrinkage. So that's something, in terms of the curing and all that, that could be taken into consideration. We didn't see a lot of issues for the girders that we looked at, but we did try to quantify those measures to include in terms of pre-stress losses and things like that. So I think the creep is less, the shrinkage is more. And so it sort of kind of comes out in the wash when you look at pre-stress losses for the mix that we were studying. And I think that's kind of been a little bit typical, but of course it can vary from mix to mix. Yeah, the total, and I think, yeah, just being able to separate that out is useful, but we didn't see any concerns with it being too high, yes.